component also has a wide range of general settings dealing with things like physics interaction. Key, given that we're dealing with kinetic pawn actors here, planar movement, and rotation, amongst others. Let's take a second to talk about rotation, which determines which direction a character faces in the game world. Different games have different needs, which, when combined with the granularity of the character and movement components, results in a huge variety of settings, some of which are mutually exclusive. It can be a lot to get to grips with. In the movement component, you'll find use controller desired rotation and orient rotation to movement, with the former orienting the character to the facing requested by their controller, while the latter orients the character towards their current movement direction. If you're orienting rotation to movement, also head over to the base character settings and make sure to uncheck use controller rotation yaw. There are also options for pitch and roll. One other thing that may not be immediately apparent to those new to the character movement component are the perch and ledge options found in the advanced walking mode settings. These determine how far out from the edge of a platform your character's capsule collision can be before it slips off, allowing you to fine-tune world traversal without having to mess with the collision itself. Finally, and perhaps most importantly, you can use the movement capability settings to determine which movement modes are available to a character, including whether they can crouch. There are also several AI and navigation settings. These we'll talk about when we get to non-player characters in the controller section. Before we move on, I want to revisit one key point from earlier. The character movement component is fully network replicated, which will save you a huge amount of time if you're planning to build a multiplayer game. The solution is mature and road-tested, utilizing a player-client predictive server-authoritative model that minimizes skipping and visual desynchronization. Now, as promised, we can finally turn our attention from our character's body to their brain, the controller. The controller is another manager class actor, again Blueprint or C++, but this one is designed to take control of, or possess, a single instance of a pawn or pawn-derived class, such as character. Once possession occurs, the controller and pawn become aware of one another, with the controller receiving event delegate notifications for many pawn events and subsequently running logic, calling functions and delegates, modifying states, and, because a controller sets the pawn view target, even taking control of the pawn's camera. That said, you most likely won't be working with the base controller itself, but rather one of its two key subclasses, player controller for player characters and AI controller for NPCs. Let's talk about the player controller and how we handle player input first. The player controller replicates from a player client to the server, but not to other player clients, which is why we recommend player state for tracking data. It is used to handle user input management and general gameplay logic relating to the player and their pawn. In terms of user input handling, the default for Unreal Engine as of the 5.1 release is Enhanced Input, our advanced input management solution, with complex input handling, runtime control remapping, and comprehensive data filtering and processing features. If you're familiar with Unreal 4's older player input solution, rest assured that Enhanced Input is backwards compatible, allowing you to cleanly upgrade to the new paradigm. That said, we recommend Enhanced Input be your starting point. Should be noted that there is also the Raw Input plugin. This allows Unreal to interface with devices incompatible with our regular input systems, such as flight sticks and steering wheels, allowing for custom input creation and mapping. Once the player controller has received the input, they can communicate appropriately with the pawn. For example, translating the X and Y output of an analog stick into movement or inventory navigation, or using the press of a button to trigger an interaction or emote. It is worth noting that, especially if you're building a simpler, single-player-only project, that you could potentially build this logic directly into the pawn, with the trade-off being that it remains locked to that specific pawn, whereas keeping the two separate allows for a lot more flexibility. Speaking of which, this is the core concept behind our AI controller, which is the next topic. On the surface, the AI controller is very similar to the player controller, a C++ or Blueprint-based manager class actor designed to interface with the pawn and direct its behavior, with all the same delegate connections and so on as described above. The principal difference here is that the controller doesn't represent a player or handle user input, and thus only exists on the server. The AI controller is not bound to a particular solution. It can run whatever logic you deem necessary for your game, be it built with Blueprint, C++, a third-party AI solution, or Unreal Engine's own behavior system. I'm going to pause for a second and talk about the behavior system, which, as a fully featured AI solution deeply integrated into the engine, may have everything you need to start building your game. At its core, the behavior system consists of an event-driven fallback state machine, the behavior tree that draws live data from its information source, the blackboard. The behavior tree is, well, a tree of tasks: move, interact, hide, linked by nodes, or composites, as we call them. The flow between these nodes is dictated using conditionals, or decorators, that determine if a node can execute. As we said earlier, this is a fallback state machine, meaning that if a decorator's check fails, it will fall back to the prior node on the tree, until it returns to the default task. In other words, a guard NPC would check to see if it sees any enemies, fall back to a patrol behavior upon seeing none, and then fall back to a default idle if they have no assigned patrol path. Since the vision check is the highest priority, it'll always get checked first and override the lower priority tasks. Decorators and tasks draw in data via the blackboard, which can be updated using services. Recurring checks hooked into AI-adjacent systems like Environment Query, EQS, and Perception. This is a powerful, flexible system, albeit one that requires some C++ to be fully utilized. For instance, if you want to add new team categories. If you're looking to do a larger scale AI implementation, for say an open world or strategy game, you could also consider using Unreal's Mass Entity system, as seen in our Matrix Awakens technical demonstration. Mass Entity is a data-oriented framework that allows you to efficiently process massive amounts of data in an optimized manner, allowing for crowds, armies, and entire cities full of cars and pedestrians. That said, even if you choose to use neither the behavior nor mass entity systems, your controller can still tap into the Unreal Engine navigation system, pathfinding, and avoidance. The navigation system is not part of the gameplay framework, but given that any AI controller is likely to be issuing movement commands, digging into pathfinding feels worthwhile. The navigation system uses a generated polygon mesh to define navigable space for AI entities. This is generally referred to as the nav mesh, with segments removed when the terrain does not meet the standards of navigability, think terrain angle, width, and so on. This nav mesh is calculated by predefined nav agents, check your project settings, within a placed nav bounds volume. Anything with collision can be set to modify the nav mesh, meaning it can be factored in by the nav agent or ignored. Be aware that using dynamic nav mesh modification to factor in mobile characters is a performance risk and not a recommended workflow. We'll get to alternate methods soon. When you ask an AI character to move to a location and have use pathfinding set to true, they plot a path using their assigned navigation mesh, appearing to intelligently navigate your game space. As such, the decisions you make regarding nav mesh generation can have a huge impact on your game. For example, you could consider using multiple nav agents to accommodate characters of differing scale within the same game space. Think humans versus vehicles, but be aware that you'll be generating a nav mesh per nav agent type, which can get costly. Adding further granularity is the ability to create and assign different classes of navigable space, which can be prioritized by the navigation system. For example, an AI character may prefer dry land over water, but both over sticky mud. Multiple nav meshes can be linked by navigation proxy links, which create a bridge between the meshes your NPCs can navigate. If you want to use custom behavior, such as jumping through a window, to move characters between navigation meshes, you can do so with a Smart Link subclass. Nav meshes can have varying levels of dynamism. You can have a fully dynamic nav mesh that is modified in real time by all of your actors, but doing so will likely be more expensive than having a completely static nav mesh and instead using one of Unreal Engine's avoidance systems, Reciprocal Velocity Obstacles, or RVO, and Detour Crowd Manager, which are mutually exclusive, to handle actor avoidance. It's really what works best for your project and performance goals. Ultimately, that's the same for controllers overall. What you do with them is up to you. However, if you are building something even moderately complex, or thinking about multiplayer, keeping the mind and body separate starts to make a lot more sense, especially on the AI side. You can plug the same brain into a bunch of different bodies, tweak some variables, and create a wide variety of behaviors with the same shared base. Ultimately, controllers, with their deep integration into the gameplay framework, are both a solid building block and a clean way to keep things organized and prevent duplicate functionality across characters. Our last stop is the HUD, or head-up display, which is a generic term for the system by which games display the user interface, or UI, to players. Given that a game UI consists of everything from player health and inventory to menu systems and profile management, it makes sense that it is tightly integrated into the gameplay framework and its various rule sets and data repositories. On a technical level, the HUD is displayed via a player's viewport, a non-replicated UI layer to which elements can be added or removed at your discretion. It should be noted that each player's controller will spawn a HUD actor for its player as part of the instantiation process, which can be useful, but you are by no means required to build your own UI logic there. It could be in your player controller, or anywhere else that makes sense. The UI itself can be built using the included Unreal Motion graphics system, an internal solution, or even a third-party plugin. But either way, it will need to pull data from somewhere to be useful. Given that we're tracking the game and player state already, why shouldn't that place be the gameplay framework? So, how do we get the data from our state actors to the HUD? In fact, how do we communicate with the gameplay framework at all? The good news is that the gameplay framework is so deeply integrated into the engine, it comes with a robust library of functions, Blueprint or C++, with which to interface with the gameplay framework. At the most basic level, you can get game instance, mode or state, get the player state, pawn, controller, and so on. You can even get the array of player states from the game state and go from there. Communication can be via interface, cast, or any other method that suits your project and its goals. And with that, we've reached the end of this presentation. We hope that you found it useful and wish you all the best in your future Unreal Engine endeavors.